discussing one of the events I attended here at PSI, the Scherrer Institute, which is a general research institute. It has physics and chemistry people there. I attended a Synfuel Symposium, Synthetic Fuel Symposium, and the concept of synthetic fuel is how to get fuel out of methane. Methane is an intermediary that comes from either biomass or natural gas. And some of the presentations, they were about how to actually have biofuel reactors. Some presentations were how to generate catalysts to get intermediates out of either biomass or nat gas that then can be further processed into hydrocarbons. There was particularly one presentation that I think was incredibly interesting. Vladimir Paunovic is a postdoc now at ETH. He's one of those people that, you know, you can see he's good. And it doesn't matter what field, it doesn't matter whether you understand the field better or worse. You know, it's like he's the Sergey Levin type. He gets to the point, he understands what he's talking about. He's very, very shy with acronyms, although the field is full of acronyms, so he also has it, but that's okay. But I think what's much, much more important is he's able to get the message across. Like, this is the problem. We have a bunch of, let's say, gas, whether it's nat gas or biomass, doesn't matter. We have methane, and we got to turn methane into methanol. And then from there, we go to olefins and then hydrocarbons. So we have methanol, and we can use that for something else, let's say for chemicals. He was talking about the catalyst design. So how can catalytic converters be designed in a more intelligent way? Sort of think of catalytic converters are kind of like the enzymes of petrochemistry. So how can we facilitate reactions? And then also he was talking in his particular talk a lot about formaldehyde, which forms while in this case, nat gas is being processed into methane and then olefins and hydrocarbons, and things build, alkaline metals. I'm not familiar with. I don't want to throw these words around. I'll put the paper and the presentation in the show notes. But what's really important here is, I think first, it was a good symposium for me to get a sense for where the field stands, right? What is this whole synfuel situation about? And it's really about designing the environment for bioreactors, whether you have biomass or nat gas. It's the same problem. Of course, with biomass, it's a little bit, there's more organic stuff there. So you have, for example, in one of the presentations, they were talking about the kind of the flow rate that goes in there, the water content, the material, the coating of the reservoir. All of these things can have influences, and this is really important also. It made me think of the dry coating technology of Tesla. There's a lot of that kind of chemical engineering going into these types of problems. But I think in general, I want to emphasize particularly one presentation by the gentleman by the name of Vladimir Paunovic. Is a postdoc at ETH Zurich. He really has this, like I said, he has a very natural way to talk about these things very useful. This is not even wrong podcast. It's February 7th, 2024. This is Krintelko. This is the second installment of today. For the year, we are down 19.6%. The market is up 3.8%, but underperforming by 23.4%. So let's talk a little bit about this symposium. Again, the symposium, the problem is, okay, where does the syn fuel industry stand in general? Synthetic fuels are fuels that are one out of methane. Methane can be gained from biomass or nat gas. So when we talk synfuel, we really talk both. We talk fossil fuel feedstocks and organic feedstocks. So they both work. And this is one of the big important takeaways from this symposium, is that you can have an intermediary, which is methane, and you can then turn that into methanol, and then olefins, and then hydrocarbons. This is sort of the process. And whether you start with biomass, whether you start with rotten wood and leaves, or whether you start with nat gas, it doesn't really make a big of a difference, because think about it, nat gas is just rotten leaves, rotten animals over millions of years. So it's the same thing, and you could kind of replicate nat gas by taking biomass and just using a lot of pressure. So you could do that, but that was not part of this talk. I think, excuse me, the symposium, again, there was a lot of operational engineering talks. For example, there was one talk, they were talking about, how to even, how to measure what's called operando drift. So when you put, let's say, biomass in a reactor and you want to gain methane out of it, you have parameters changing during the reaction, and you can do spectroscopy to monitor that. So part of the work here is just people using tools such as spectroscopy to monitor the operando drift, which is really how do things change. And I want to use Vladimir's presentation as an example to illustrate my point. So what Vladimir was talking about is the coke formation in the process of generating methanol out of methane. Before I go there, I just want to quickly make clear that it's understood what we're talking about here. Again, we have a feedstock, whether it's biomass or nat gas. We extract methane from there. We can either have it, I think nat gas probably is already methane, I'm not sure, but you somehow have to get to methane. Then you turn methane into methanol. You then extract olefins from there, and then you go to hydrocarbons. That's for the fuel production. So in this context now, Vladimir was talking about coke formation. And in particular, he looks at the question is, what kind of catalysts can be used in the process of methanol production that that reduce coke formation. Coke is a bad thing. Think of it like a bad thing. So this is one example of where you can, again, you can use physics parameters such as flow rate, pressure, temperature, water content, fluidity, viscosity, all kinds of things. And you can also look at, for example, what's called isomerization, which is when the process, the chemical species stays the same, but the three-dimensional spatial representation changes, and that can have influences on coke formation. He particularly used formaldehyde formation, which is sort of an intermediary that is produced within the methane to methanol process, and he was following that sort of line because he has a conjecture that formaldehyde helps coke formation. So what provokes formaldehyde formation? Formaldehyde is good and bad things. So there's an optimal amount of formaldehyde you can have in a process. And then you want to study what this additional formaldehyde, what it does to the coke formation. Use spectroscopy. You look at spatial representation. You want to understand the structure of the coke building. Where is it building? What kind of crystals is it attaching to versus not attaching to? So there, a lot of, like I said, electrospectroscopy, other types of measurement technologies, such as X-ray tomography, atomic tomography, electron diffraction, X-ray tomography, which is kind of like a CT scan. So you use X-rays to get a three-dimensional representation. Then you can use computational methods to improve that. That's work that I've been looking at in the Stanford electrotechnic seminars. So I just mentioned this. I think the actual measurement technique, the measurement techniques themselves are already pretty interesting. But Vladimir was using them to measure the coke building within the methane to methanol process, and it's really interesting for a couple of reasons. One is you can kind of get a sense for where the industry stands. It's still in the early days because also there were some questions. Let's say coke itself is a very toxic material. So do you really want to have a synfuel industry that creates a byproduct like that? Vladimir said, look, I mean, you have byproducts like that in every kind of petrochemical industry. Therefore, I think we're still better off having more flexibility using methane from different feedstocks than just basically making hydrocarbon out of crude oil. So Vladimir's PhD thesis, by the way, was how to extract fuel from nat gas. He looks at specific chemical compound that could be used as catalysts in that particular endeavor. And I think a lot of his work is actually what's called heterogeneous catalysts, which is, okay, you want to catalyze these processes so you can get to the desired results. And heterogeneous just means different phase. So if you have a fluid, you want to use a solid or a gaseous catalyst. If you have a gas, you want to use a solid or a fuel catalyst. That helps in separating the catalyst from the actual chemical specimen, and is also easier to dispose of toxicity and things along those lines. So I think to summarize, I think the symposium, again, it was very interesting because it gives you a good sense for where chemical engineering is being applied in the synfuel space. In particular, it's being applied in sort of the whole, okay, what kind of reactors can be built for fuel production, what kind of coating do we use, what kind of pressure, what kind of temperature. There's a lot of try and error, and then there's also the catalyst question. Now, I want to finish this summary of the symposium just with some thoughts. And those thoughts are about computational chemistry. And the way I think about it is the following. I think that, like in any other field at this point, we could ask the question, how much in silico design can we have? And I just spoke about this in the previous episode, that we could potentially have this massive try and error endeavor, in this case, the synfuel industry, and we can try to simulate it in silico and use in silico design to iterate faster. I haven't spoken about this with the people in the symposium. I think I should have. I think that was a mistake, and next time I should stay longer and talk to people about it, because it's really an interesting problem, right? You have these massive reactors, you have these big physics elements, again, flow rate, pressure, temperature, viscosity, all kinds of things that play a role in the physical process of synfuel production. And the question is, could you potentially use in silico design, or at least have physics simulations be more directly applied to the iterative process? Jensen said that in the chip design, you almost have a perfect chip and it's ready for tape out. Could we get there with synfuel design? Is that a possibility? I think this is a path, and I'm going to monitor this closer. I think, again, the applications are massive. You can have physics simulations. And then on the catalyst design is kind of similar like the pharmaceutical design, right? Catalyst design, there's another level of abstraction there, which is, okay, once you have the best physical surroundings, or the best physics applied to the process of methane to methanol production, well, then what kind of catalysts could you use, and how do catalysts interact with the specimen given the physics? So those are the kinds of questions that come up. Those are the kinds of takeaways, and I think it's a very interesting field that I'm going to keep monitoring. Thank you.